Hi everyone! Today we're continuing chapter 16. And first, I wanted to review a problem that we did last time on your worksheet. So on worksheet problem 4, we were determining the hydronium ion concentration and pH of a 0.2 molar solution of formic acid. And I told you that the acid ionization constant for formic acid was 1.8 times 10 to the negative fourth. So first we started out by writing the equation between the acid and water. And then we used that equation to write out an ice table. And the ice table told us the equilibrium constant expressions for each reactant and product. Then we wrote out the acid ionization constant expression and plugged in the values for each. And in this case, we assumed that x was really small, so we ignored the change in x in the denominator. And then we solved for x, which was equal to the concentration of hydronium ions. And then we checked that our assumption was correct. And then we calculated the pH. Now, I wanted to go over this because this is going to come up again, so just keep this problem in mind. Now, last time we went over one way to solve for the concentration of hydronium ions and therefore figure out the pH or the strength of an acid. Another way to measure the strength of an acid is to determine the percentage of acid molecules that ionize when dissolved in water. And this is called the percent ionization. So the way that we calculate this is shown below. Percent ionization is equal to the concentration of ionized acid over the initial concentration of acid, and then we multiply that ratio by 100. And you'll probably notice that this equation looks really familiar. And in fact, if we go back to our problem from last time, you'll notice that when we checked our assumption and whether it was valid, we did the same exact thing. We took the concentration of hydronium ions at equilibrium and then divided that by the initial concentration of acid and multiplied by 100. So you've already performed this calculation before. Now, one thing to keep in mind is that if the percent ionization is really large, that means you have a really strong acid. So, for example, hydrochloric acid, which we know by now is really strong, it completely dissociates in water. So that means it would have a really high percent ionization. And in fact, the percent ionization would be 100. So in that instance, the concentration of ionized acid would equal the concentration of hydronium ions in solution. So let's go through an example of how to find the percent ionization of a weak acid. And we're going to use the example of formic acid again. This time, though, the concentration is much higher than what we calculated in worksheet problem 4. So the concentration this time is 2.5 moles per liter. I'm going to change my marker color here. So we're going to start out with exactly the same steps that we performed last time. We're going to write out the chemical equation. And then I'm just going to add in the states here. Okay, And then we're going to use this equation to write out an ice table. And just like last time, I'm going to separate my reactant from my products. Okay, so we're going to fill in the initial row. And again, we were told that the initial concentration of formic acid was 2.5 moles per liter. And then we don't have any product initially, although remember that we do have a very, very tiny amount of the hydronium ions just from the autoionization of water. However, this isn't going to contribute to our overall concentration to a significant extent, so we're just going to put approximately 0 under the hydronium ion concentration. Okay, and then for change, we're losing some amount of our reactant, and then that reactant is becoming product, so we are gaining some amount of product. And we're just showing that change as X. And then we're going to add up the first two rows to get our equilibrium expressions for each. And now we're going to do the same thing we did before. We're going to write out our acid ionization expression. And the next step is to input the acid ionization constant and then the equilibrium expressions for each of the reactants and products. Oh, ignore this. That should say formic acid. The typo. Okay, so let's rewrite the acid ionization expression here. There we go. And when we were working on worksheet problem 4, we said that the acid ionization constant was 1.8 times 10 to the negative fourth. And then we can now plug in each of our equilibrium expressions. So we have x times x for the products, which is just x squared. And then we're dividing that by 2.5 minus x. Now, again, we're going to assume that x is small, and hopefully that is true, and we don't have to use the quadratic formula. So I'm just going to cross out the x in the denominator. We're going to assume that it's not going to have a large impact on the initial concentration. Okay, so now we're just going to perform our calculation here and solve for x. And you should get that x is equal to 0.021. And remember that x is also equal to the concentration of hydronium ions at equilibrium. So I'll put a little EQ next to the concentration of hydronium. Now, our ultimate goal here was to calculate the percent ionization of this solution. So I'm going to now calculate the ratio of hydronium ion concentration at equilibrium all over the initial concentration of the acid. And then we'll multiply that by 100. Now remember, this is also going to be a good check of whether we can assume that X is small or not. So I'm going to put in parentheses under percent ionization that this is also our check step. Okay, so this will equal 0.021 divided by 2.5, and then we'll multiply that whole thing by 100. And we should get a value, oh, sorry, let me go back. We should get a value of 0.85%. So not only does that tell us that our assumption is valid, but we also determined the percent ionization of this weak acid solution. Now, the fact that the percent ionization is really small does make sense for this solution because formic acid is a weak acid. So we don't really expect it to ionize to a significant extent. Additionally, though, let's just compare this to some previous results. So we're going to look at the relationship between the equilibrium concentration of hydronium ions and the initial concentration of the acid. Now, if we increase the initial concentration of acid, then that's going to result in increased hydronium ion concentration at equilibrium. However, what's really interesting here is that increasing the initial concentration of acid results in a decreased percent ionization. So this means that the increase in hydronium ion concentration is slower than the increase in acid concentration. So let's kind of dive into that a little bit further, because it can be a little bit confusing to kind of wrap your head around the fact that there isn't really a linear relationship between these two things. Okay, so let's make a little table, and we're going to make a table of formic acid concentration, and this will be the initial concentration. And then we're going to compare that to the concentration of hydronium ions at equilibrium. And then we're also going to compare that to percent ionization. So from worksheet problem 4, we saw that the initial concentration of formic acid was 0.2 moles per liter. And we had calculated the concentration of hydronium ions at equilibrium to be 0.006 moles per liter. And if we look at our calculation for checking our assumption, that's the same as the percent ionization. So we know that the percent ionization here was 3%. Now let's look at the example on the last slide. Oh. So we said that the initial concentration for that example was 2.5 moles per liter. And we calculated the hydronium ion concentration as 0.021 moles per liter. And the percent ionization was 0.85%. Okay, so this is a little strange. We can see that the concentration of formic acid is increasing, and we can see that as a result, the concentration of hydronium ions is also increasing, but the percent ionization is decreasing. So this is not a linear relationship. So why? Why doesn't the percent ionization increase if we're ending up with more hydronium ions at equilibrium? So this has to do with Le Chatelier's principle, which we learned about in chapter 15. So if we imagine just a generic acid and it's ionizing into hydronium ions or hydrogen ions and its conjugate base, remember that if we add more product, so that's essentially what we're doing here. We're increasing the concentration of the acid, which is increasing the hydronium ion concentration, which is the product. We're going to see a shift to the left, or we're going to see a shift towards the reactants. So that's going to actually decrease the amount of ionization that's actually taking place. Another way to think about it is in terms of volume. If we're adding more of our initial acid, we're decreasing the amount of volume available. And so the reaction is going to shift towards the side with less molecules, and that's going to be the reactant side. So the main thing here to remember is that even if your concentration of hydronium ions is increasing, that doesn't necessarily mean that the percent ionization is increasing. And in fact, it's going to decrease. So now let's talk about finding the pH of mixtures of acids. Now, we talked about how to find the pH of a strong acid. We know that the concentration of hydronium ions will equal the concentration of the acid because there's complete ionization. But then for a weak acid, to find the pH, we have to go through that whole process of setting up an ice table and then solving for X in our equilibrium expression. So what if we have a mixture of a strong acid with a weak acid? Now again, the strong acid is going to completely ionize, and that's going to provide more than enough hydrogen ions or hydronium ions to shift the weak acid equilibrium to the left. And therefore, any contribution of the weak acid's hydronium ion concentration is negligible. So let's look at an example. Let's say that we have 0.2 molar hydrochloric acid. And we also have 0.2 molar formic acid, which is a weak acid. So again, remember that HCl is strong and formic acid is weak. So we already said that the concentration of a strong acid is equal to the concentration of hydronium ions in solution. And then we said previously that the concentration of a weak acid is much, much greater than the concentration of hydronium ions at equilibrium. So for the 0.2 molar HCl, the concentration of hydronium ions is equal to 0.2 moles per liter. And from our worksheet problem 4, we saw that the concentration of hydronium ions at equilibrium for a 0.2 molar formic acid solution is equal to 0.006 moles per liter. So the concentration of hydronium ions from our weak acid is negligible compared to the concentration of hydronium ions from the strong acid. But additionally, remember from Le Chatelier's principle, if we add a bunch of hydronium ions to solution, so for instance, if we have a bunch of hydronium ions from our strong acid, that's going to drive the reaction to the left. So because we already have so many hydronium ions from the strong acid, the weak acid doesn't have to or won't feel compelled to produce any hydronium ions. Now, what if we have a mixture of weak acids? So we're going to generally consider only the stronger acid for the same reasons that we said before. And this really only works as long as one acid is significantly stronger than the other and their concentrations are similar. So let's say that we have a mixture of 0.2 molar hydrofluoric acid and we have 0.2 molar perchloric or hypochlorous acid. Oh, I'm writing the wrong thing. Let me fix that. So HClO is hypochlorous acid. Now, the acid ionization constant for hydrofluoric acid is 6.8 times 10 to the negative fourth. So hydrofluoric acid is weak. And then the Ka value for hypochlorous acid is 2.9 times 10 to the negative eighth. So hypochlorous acid is very weak. Now, if we have a mixture of these two, hydrofluoric acid is the stronger acid. Even though it's a weak acid. So its concentration of hydronium ions at equilibrium is going to outweigh any contribution of hypochlorous acid hydronium ions. So to calculate the concentration of hydronium ions for this mixture, only consider the contribution from HF. So again, if you have a mixture of weak acids, we're only going to consider the contribution of hydronium ions from the stronger acid out of the two. But again, this only works if one is significantly stronger than the other and if their concentrations are similar. Okay, now let's just do one more practice problem before we end the video. We're going to determine the percent ionization of a 0.225 molar solution of benzoic acid, which is HC7H5O2. And if you want to pause the video and try this problem on your own, you can. And then when you restart the video, we'll work on the problem together. Okay, so let's try this problem. So again, the first thing we should always do is write out the chemical reaction equation. So I've got my acid, which is benzoic acid, and that's going to react with water. And benzoic acid, of course, is an acid. It's in the name. And then water is the base. So the acid is going to donate a hydrogen ion to the base. So we'll end up with our conjugate base, which is C7H5O2-, and then the conjugate acid, which is H3O+. And now we can use this equation to help us write out our ice table. Okay, so I'm separating my reactant from my products. And again, we're not including water because its concentration doesn't change since it's a pure liquid. And the initial concentration of the acid is 0.225 moles per liter. And we don't have any of the products, or at least we have approximately 0. And we don't have any complicated stoichiometry here. Everything's 1-to-1. So when we're considering the change, we just have minus x and then plus x and plus x. And then we're going to add those two rows together to get our equilibrium expressions for each reactant and product. Okay. So now the next step is to write out the acid ionization constant expression and plug in the values. Oh, whoops. I guess I didn't give myself another slide to work on, so we'll try to squeeze that in here. So I'll use a different color for this next step. So for this problem, Ka will equal the products over the reactants. And in your worksheet problem, we're told that the Ka of benzoic acid is 6.5 times 10 to the negative fifth. And we're going to plug in x and x for the numerators, that's x squared. And in the denominator, we have 0.225 minus x. Now, again, we're going to assume that the change in x is small. So we can ignore that change in x. And then if you solve for x, we should get a value of 0.0038. Whoa, my pen wants to write in bold, apparently. And then that value of x is also equal to the concentration of hydronium ions. So now we have to calculate the percent ionization. And actually, I think I'm going to add in a slide here because we're running out of space. So let's insert a new slide. So now let's figure out the percent ionization. So we said that the concentration of hydronium ions at equilibrium is equal to 0.0038. So now the percent ionization is going to equal the concentration of hydronium ions at equilibrium over the concentration of our acid initially. And then we multiply that by 100. So plugging in that value that we found before, we have 0.0038 divided by 0.225. Now remember that this percent ionization calculation is also going to check the validity of our assumption that X is small. So as long as this percent is less than 5%, then we know that the assumption is valid. Now, plugging this into a calculator, we should find that the percent ionization is 1.7. So that tells us that our assumption is valid, but additionally, we figured out how much of this acid ionizes in solution. Okay. Now, I do have some optional problems for you to try if you want some extra practice. So in the TRO textbook, the 4th edition, I recommend doing problems 47, 57, 63, 71, 73, and 89. And these problems in particular are highlighted in blue, and so they have answers in the back of the textbook if you want to check your work. Unfortunately, these problems don't really explain how to solve the problem, so if you do have questions on that, or if you're getting lost during the problem, feel free to email me or set up an appointment with me on Calendly, and we'll talk over the Zoom app. All right, I will see you in the next video.